Morning, everyone. Thank you for joining my talk today. I'm Zhu Zhang from Chongqing University of Post and Telecommunication, presenting our work Adversarial Data Augmentation for Single-Domain Generalization via Lyapunov Exponent-Guided Optimization. My report is divided into 5 parts. First, I will introduce the motivation behind us, and then the methodology and the experimental results, and finally conclusion and future work. Let's start with the motivation. Single Domain Generalization, or SDG, asks a simple but important question. Can we train a model on one source domain and make it work across many unseen targets? In the real-world image to cartoons, the domain shifts are massive. The core goal is clear. Build a model that doesn't overfit to source domain. Existing augmentation tricks help, but they often stick to local tweaks, missing the big features in parameter space. So, borrowing from the dynamical system theory, treating training as a chaotic process and guided to the edge of the chaos. That sweet spot where the system is flexible but not widely stable. Our insight is to use the Lyapunov exponent to measure and steer this, enabling deeper, more global searches. This unites stability and explanation in SDG. So how do we make it happen? Let's move to the methodology part. We model training dynamics as a discrete time systems. Model with equals like zeta t1 equals zeta t minus zeta delta L zeta t. The Lyapunov exponent lambda capture the sensitive how tiny permutation is below over iteration. Here, high lambda means chaos, training diverse impractically, while the low lambda means the training is the system is too stable, no adaptability. Our target is to make the lambda approaches 0, which is means the status of the edge of chaos for optimal generalization performance. We estimate lambda by checking permutation groups. Start with very small delta theta, iterate and compute the exponent while the log of expansion rates. Although this is very simple but it's powerful, keeps our optimization balance. Let's see how we adapt it. And this is the adaptive learning rates for chaos edge training. We dynamically adjust the learning rate based on the change in the Lyapunov exponent. And we also covering LE control with the adversarial augmentation. We use the adversarial samples, which is generated by the semantic transformations. And we also use the LE guided optimization to stabilize training by keeping the systems near the edge of the chaos. And we join these two optimization objectives. Okay, let's turn to the results. We tested on three SDG benchmarks, and our method achieves SOTA results on these three standard SDG benchmarks, showing consistent improvements. Especially, we get 2.32% over the PACS dataset and 1.78% improvement over the Office's home dataset. And these gains demonstrating the effectiveness of our methods. And we also tested our methods in low data scenarios. With only 10% of the PACS training data, our method still deliver a 9.47% accuracy over the strongest baseline. And this shows the effectiveness of our methods, especially when the data is scarce. And we also, to isolate our contribution, we also abruptly optimizes while keeping augmentation fixed. We change our optimizer with other common or typical optimizer like ADAM and ADAM WMSDD. And we can observe that our LE aware SGD still shows the performance gains even use the common optimizers. And we also perform the hyperparameter sensitivity experiments, which we can observe that our methods perform well over a range of values in parameters, indicating ease of tuning of our method. And our method is also comparable with the strongest baseline ADVST in terms of the computation cost. Finally, our method can be regarded as a plug and play optimizer boost methods. And we also incorporate our proposed optimization framework into the ADA or MEADA or ADVST. And we can observe consistent gains in these methods. And finally, let's make a conclusion and for future work. In summary, our key contribution novel lens on SDG, unify stability and plasticity a simple LR rule for edge of chaos training, and consistent against a log-cross benchmarks. And in future world, we will investigate scaling to ImageNet size SDG, or tackling detection or segmentation instead of only for classification tasks. And we also explore layer-wise Lyapunov schedule for final control. And test bigger backbones like ResNet 101 or 152. And that's all about my today's presentation. Thank you for your attention.